Hi everyone, I'm Carina, and I will be presenting my internship project regarding image classification on the cloud with the HPCC Systems GNN bundle. Here, I just wanted to give an overview of the contents of this presentation. So I'll go through a quick introduction about myself and my project, and then describe some of the terminology and concepts used. In the third section, we'll basically talk about how I procured the student image dataset to train my machine learning model, and also the security protocols I followed to ensure compliance with LexisNexis policies, but also my school policies when working with student data. And we'll get into more of that later. Next, we'll get into the portion of the project that was done in the local environment using transfer learning TensorFlow models on Jupyter Notebook. In this section, there was quite a bit of trial and error when evaluating various models to ultimately select the one with optimum training speed and accuracy. And essentially, these findings will allow future users of the HPCC Systems GNN bundle to automatically test their dataset on the quickest and most successful model. The arguably most important set of findings came from section 5, where I explained training on the cloud and the JIRAs that I opened. And finally, we'll go through a flowchart I created that kind of streamlines a clear process reflecting the findings of my internship project for students at AHS, and also anyone else in the wider community who wants to use the HPCC Systems GNN bundle. A brief introduction. A little bit about me. I'm going into 11th grade at American Heritage High School, and this is abbreviated AHS. This abbreviation does come up quite a bit when talking about student data, so just know that I'm referring to my school. And at my school, we've built an autonomous security robot with a myriad of capabilities, and some of those are listed here, like the touchscreen, voice commands, fingerprint recognition, and more. The computer image of the robot is shown here on the left. And basically the vision for this robot is for it to drive around campus autonomously. And any student can view school information, visitors can print out temporary IDs, anyone can ask the robot any questions they might have. And ideally, this system will also assist security officers in kind of having a better idea of who is on campus and specifically where they are. So in case they need to contact someone or find someone in an emergency. In order for this to come to fruition, there needs to be a student database and a way for security personnel sitting in their office to identify whether the person standing in front of the robot is a student or not. And that's where this internship project comes in. So I collected and tested around 4,800 student images, so 8 students and 4 non-students, by training a model to output AHS student or not an AHS student based on the individual it detects in the image. And I was also able to output the student and visitor's individual specific ID number. The long-term goal is to process mass amounts of student, staff, and visitor images with HPCC Systems, since one of its strengths is big data processing. And in order to set this up, my project evaluated various models to increase accuracy and ultimately train these models faster. On the HPCC Systems side, the purpose of this project was to identify any bugs and improvements in the GNN bundle, especially on Azure as HPCC Systems transitions from bare metal to the cloud. And like I mentioned before, I also developed a standard procedure for using this HPCC Systems GNN bundle, both locally and on the cloud for all future users. So here's a really cool video that kind of shows our vision for this robot. The company in this video is using it in a park setting, but we wanted to build our own version of this robot for much cheaper and also for school use. As you can see, there are a lot of cool features with this security robot, and we're continuously adding new capabilities that you saw in the video to our school robot, and the possibilities are endless. So I obtained and classified images of actual students, teachers, parents, and visitors. And this basically made it more realistic and allowed me to test various models accurately by using a data set that represents actual images that our robot would capture. So I used industry standard models in addition to the GNN bundle version 2. And I tested these models on my PC and on Azure. The general purpose was to test the cloud and tweak parameters to optimize the model's capabilities. Everything from this project is applicable to anyone in the wider community using the HPCC Systems GNN bundle. So now for some quick descriptions. What is an artificial neural network? So initially it simulated a human brain, and it's ideal for large, complex machine learning tasks. So some things we might be familiar with are Google Images or Siri voice recognition or YouTube recommendations. And the objective of model training is to minimize losses and improve the model's overall accuracy. So then what are CNNs? CNNs emerge from the study of human vision, and they're particularly used in image recognition because it efficiently processes pixel data. One difference between CNNs and other neural networks is that the convolutional layer usually isn't fully connected. What does this mean? So in the image in the bottom right, perceptrons in the 3 pink layers only receive a small portion of the input. And the top 2 diagrams show the difference between being fully connected, which is the top diagram, and not fully connected, which is the one in the middle. So then what are GNNs? GNNs are the HPCC Systems implementation of deep neural networks, and this also supports CNN. The good thing about using GNN is that it coordinates Keras and TensorFlow. And finally, image classification is just what the title suggests. These models analyze images and identifies which class they belong to. Now let's talk about obtaining images for these classification models. What separates this project from most standard machine learning is the mechanism for obtaining data. So the general workflow is shown in this graphic. A person would stand in front of the camera on the security robot. And instead of artificially changing the angle of a person's head tilt in the image, I took videos with a robot camera. So each person moved their head in circles, kind of like what your iPhone makes you do when setting up Face ID. And the purpose of this is to simulate real images that the robot would capture from the exact angle that the camera is sitting at. The camera's video then goes to a computer where it's converted into thousands of still images using a program called VLC. I needed a lot of photos so I could build a large enough data set to really test HPCC Systems Thor functionality. And the video to still image process was nice for this because it produced 30 frames per second. It also set up the long-term project and drastically expands the number of real images and real data that I had. On this slide, I also have the specific image size, 224 by 224, which is pretty standard for most image classification models, and BMP, because that's the file currently supported by GNN. Using Azure to process images that come from a school setting required some additional security protocols. So this project generated a new form with my school's legal team that now grants permission to process student images. We also filled out the LexisNexis Azure Access Request form to basically ensure compliance on both fronts. And of course, other security protocols like blurring student images for public presentations and identifying with fake student IDs instead of names were also utilized. With all this set up, what did training a model in the local environment actually look like? So here are the various models that I tested in Jupyter Notebook and their respective training times. All of the models that I used are mature, industry standard models listed in Keras applications, and they're all backed up by published research papers. The models also all support the TensorFlow latest version and achieved 100% accuracy by the second epoch for my dataset, so 2 iterations. MobileNet v2 ended up being the quickest, so all future testing on Jupyter Notebook and on the cloud used this model. A little bit more about the MobileNet v2 model. So if you want to learn more about it, you can reference this published paper. Basically, the highlight of the MobileNet v2 model is the design of the 88 layers. It specializes in balancing accuracy and efficiency by basically reducing the amount of operations and memory needed to achieve that same high accuracy rate. The model is particularly efficient with memory usage, and that's basically important for increasing processing speed, which is essential on a robot setting. Here's some screenshots of the Jupyter Notebook model I trained on my PC, which I've also included in my Mac specs for reference. So the sections I want to point out are where it says, found 4,840 files belonging to 12 classes, using 3,872 files for training. So what this tells us is that the rest of these images are saved for the test set, which is used when predicting images, and we'll go into that on the next slide. The 12 classes are displayed as S, 1, 2, 3, 4, 5, and then a number, or X, and then a number. And these are each of the individuals that the model recognizes. At the bottom, you can see where the code says feature extractor model. Changing this link is how you would load a different model. So right now it's set to MobileNet v2. On the bottom right, these are the results displayed. So I currently have it set to 5 epochs, which as you can see, took around 40 seconds each. And the first epoch already reached 100% accuracy. This is where we can evaluate the model performance and predictions. So the chart on the left shows the loss function, which minimized pretty quickly. And the chart in the middle shows the accuracy exponentially increasing to 100% around the same time that the loss goes down to nearly 0. The final image on the right shows the model predictions with the images in the test set. So like we were talking about before, these are the images that were not used for training. And it outputs the student number or the visitor number, and all the predictions ended up being correct. So now that we trained a model on Jupyter Notebook, what does it look like on the cloud? The first part was setting up the Kubernetes environment. So the 2 regions I used were Canada Central and Central India. The specifics are shown on the slide, but in the interest of time, we'll just cover the general info. I used spot instances and tested various HPCC Systems platform versions. The next step was deploying HPCC Systems and spraying the data. So I used a storage account in shares, with the reason basically being that it relinquishes the need to continuously re-upload the same dataset. Here are the commands to deploy storage and deploy HPCC Systems. Keep in mind that I used platform GNN, which includes TensorFlow and related libraries. When spraying and uploading the data, since with a large dataset, it would be a little hard to complete from ECL Watch, I sprayed the data via the command line. I have the main code that trained the GNN model displayed here. I modified this GNN model to allow for loading the pre-trained MobileNet v2 model that, as you saw, was pretty successful when tested locally. At first, this code didn't work, but after playing around with it, I found out that commenting out the metrics and sort outputs allowed it to run. But let's say that you do want to output these things. There's actually a new solution. So a little bit of background. With this dataset, TensorFlow needs around 6 gigabytes of memory, and Thor and GNN need at least 6 more gigabytes. The problem is that no matter what you set the memory to, Thor will use up most of it and not leave enough for TensorFlow. So the solution is to create a parameter called global memory size to control the amount of memory Thor workers can use. Set global memory size to the maximum number of gigabytes Thor and GNN will need. So for example, if you set worker resources memory to 16 gigabytes and set global memory size to 10 gigabytes, this would leave 6 gigabytes for TensorFlow. Otherwise, you'll get an error message that says OOM killed, which means that it's out of memory. The next stage of testing involved changing the number of Thor workers. So for all of these trials, a few variables were held constant. All of them used 5 epochs, with the image size being 224 by 224 by 3, and the model set to MobileNet v2. So with all of this held constant, that tells us that any change in the training time is directly attributable to the number of Thor workers that we changed. These 2 images of the command line in ECL Watch are examples of what one trial looks like. So as you can see, the accuracy reached 100%. And on ECL Watch, it displays the epoch number and the loss, which in this example went down to nearly 0. At the bottom, this is where it displays that the trial is completed and the total cluster time. I created the two charts on the right to organize the findings of these trials. And as we could expect, when the number of Thor workers increases, the amount of time needed decreases because it's basically using more resources to process that same amount of data. Up to this point, I've mostly used 5 epochs for each test. Since the models usually reach 100% accuracy within the first 2 epochs, there was really no need to wait and run 100 epochs every time. But I did run one long Thor HPCC Systems GNN test. Since HPCC Systems is known for processing big data, I wanted to ensure that any developments for my project would be applicable when magnifying the dataset. So this longer test used 100 epochs, 4 Thor workers, each with 4 CPU and 8 gig memory, and the same batch size of 32. It ended up taking around 5 hours, and there were no errors displayed in ECL Watch. The test completed with expected performance results, reaching 100%, and this basically set up any future project using the HPCC Systems GNN model on the cloud. These images on the right also show the resources and the setup, the epoch number and loss function, which you can see here, it went up to 100 epochs, and the total cluster time once the work unit was completed. Here's a little bit about the cost for running AKS. Before using a spot instance, it got really expensive, but after making that decision, as you can see, it was much cheaper. So keeping the image data and work units on the cloud for 14 days cost around $4 with a storage account. This will basically save all of my previous work units and sprayed images. Other developers can also look at your work units and reuse your sprayed data. Testing in the last 4 days of my internship, including the long Thor test, cost around $35. And for the final section, the flowcharts and JIRA tickets that I opened. I could spend an entire presentation on these 2 flowcharts, but in the interest of time, I'm just going to go through the highlights. So the flowchart on the left details the procedure for collecting images, especially for my school's dataset. It explains everything from taking the video to converting it to still images using VLC, and then running my Java program to resize, crop, and change the file type. The flowchart on the right is generic for anyone wishing to use the HPCC Systems GNN model, either on the cloud or locally. It explains how to set up everything, prepare GNN development, develop the GNN model and train with data, and also finally predict a new image. And here's an overview of the JIRAs that I opened. So throughout this internship, I opened 15 JIRA tickets with some of the major bugs resolved and documented 8 bugs and 7 improvements, with all of them enhancing the HPCC Systems cloud platform. So there are several importances with resolving some of these JIRA tickets. First, through this whole process, the GNN bundle was evaluated with development, training, and execution-related tasks improved. Performance limitations were also identified through comparisons with local testing, and improvements to user compatibility were discussed. The out-of-memory error message and the index out-of-range error message in the GNN training code were also both resolved. And the arguably most important contribution was the improvement of the GNN bundle to support Keras applications. And essentially, this allows for usage of accurate and reliable industry-standard models instead of requiring users to develop one themselves or be limited in options. And in the long term, this greatly increases the efficiency of GNN model development. If you would like to implement something like this yourself, here are the links to my GitHub with a detailed README file to guide you through everything, my personal blog, and a folder with all the flowcharts that I created for a concise, big picture overview. I will also have a blog post on the HPCC Systems website, which will be more tutorial style with embedded code. The main takeaways from this project include getting security clearances. So without permission, we wouldn't be able to process any of these student images. There was also the decision to blur images for public presentations and only use numbers instead of names. And basically this turned it into actual implementation instead of just a proof of concept. And we also generated a new security release form. Another takeaway was developing the instructions for all HPCC Systems GNN users, which any integration with HPCC Systems and AHS will also benefit from this. We also found that using an industry standard model can achieve peak performance results. And this work tested GNN and Thor clusters to train a dataset on the cloud, which addressed some bugs and improvements. A possible continuation of this project would involve using a similar process for, say, object detection. And in the future, the same system could be used for license plate recognition or to automate this entire process of classifying images on the robot for new students. Thank you all so much for watching our presentation, and feel free to contact me with any questions or comments. Thanks again, and have a great day.